Good morning,
Good morning.
ladies and gentlemen. We're Team 3D Solar. My name is Carl Jad. These are my team members, Mohammed Arif and Christian Bernard. Our project is the three-dimensional solar panel, and our faculty advisor is Dr. Bilal El-Zahab. Now, I'll give a quick introduction into a solar cell. Solar cell research and development has been around for many years, even since the early 1800s. But in recent times, they have become more popular as a means of primary energy generation. Now, solar cells are also commonly referred to as photovoltaic cells, and the main idea behind these is to convert sunlight into usable energy via photoelectric effect. Now, this effect will be explained further down in the presentation. Now, the modern solar cell, as we know today, and as can be seen here in the picture below, can be electrically connected together to form what we know as a module, which is the illustration in the middle. And a module can also be wired together to form here what is an array. This will produce the maximum amount of energy possible. Now, these modern solar cells were first developed back in the 1950s by a company called Bell Laboratories. And the very first application of these cells were seen in 1958 at the launch of a satellite called the Vanguard 1. Now, moving on, for our problem statement, we want to address the overall carbon footprint. We want to try and reduce that by utilizing our three-dimensional geometry to basically increase energy generation. And our design will be in such a way, designed in absence of a solar tracker for the ease of installation. As we move on, our motivation for our project is fairly simple. Reducing the dependence on fossil fuels is at the top of our list. As you know, the demand for usable energy is constantly increasing. And now fossil fuels such as, for example, oil and coal will become scarce. And it is for this reason that we want to harvest as much energy from the sun as possible, because the sun, in fact, is an unlimited energy source. Now, we hope that by producing enough solar energy, that the cost of electricity will go down. And our solar panel will be designed in such a way that it is portable enough to reach basically remote areas that are off the electrical grid. And now I'll give it over to Mohammed that will further go into the presentation.
Our objective is to maximize the sunlight absorption into our design and utilize the maximum energy by implementing the 3D geometry of our design and implement the design in potential applications, and whether we can implement our design into remote areas where the power grid is not available. Moving on to global aspect of solar panel, countries around the world are moving on to renewable energy, in particular the solar energy. Countries like Germany produces 3% of its total energy from solar panels. United States was the 5th largest in 2010. Moving on. Our design goal is to manufacture or design 3D geometry at low cost and efficient. And our design, we are implementing silicon material, which is polycrystalline. This is cheaper, it's less efficient than the monocrystalline cell. Moving on.
Okay, so for our design, we chose to go with a parabolic curve geometry. And this is because the solar cell works at optimal efficiency when the sunlight hits it at or around 90 degrees. And with this geometry, it's almost always at or around 90 degrees. This is the rectangular panel that we also built, which was compared to the curved panel during our testing phase.
To check the strength of our design, we did a stress analysis of our design to see if it withstands the wind forces and pressure. We estimated our wind force and pressure to 20 Pascal, and we did a roughly estimate and did more simulation according to 40 Pascal pressure forces. As you can see, the safety factor is high, which is 36.
Okay, so how it works. So these cells are made from silicone, which is a very good semiconducting material. So it transfers the electricity efficiently. These cells are made up of two layers, a positive and a negative layer. And when the photons are absorbed from the sunlight, it creates electrons. Electrons are released into the system. The electric circuit then captures the flow of electrons, produces the current. This is called the photoelectric effect.
Now in this slide, I will be going over the positioning of our solar panel, basically on our test day. So it is common to point the solar panel in the direction of the equator, which the equator represents the red line over there in that illustration. So basically all the countries that are located in the northern hemisphere, you want to point the solar panels due south. As well as for the countries in the southern hemisphere, you want to point solar panels due north. So for our specific purpose, since we are located in Miami, Florida, and our test location is here in Miami, Florida, we pointed our solar panels due south. Now, basically, once we got the positioning down, that we wanted it pointing south, we wanted to find a way to get the correct angle to put our solar panel at to increase the energy generation. Now, since in Miami, Florida, there are different seasons, such as spring, fall, winter, and summer, there will be different angles at which to put the solar panel for optimal energy generation, basically. So, since we are currently in the spring, and we are testing in the spring, we chose our latitude for Miami, Florida, which is about 25 degrees north, and we subtracted from that the 2.5 degrees, which gave us about an approximate angle of 23.5 degrees. And that is what we set our solar panels to. So for instance, in this illustration here, we can see sun position for different seasons of the year. We can say that in the northern hemisphere, in the wintertime, we can see that the sun is at the lowest point in the sky, meaning that the tilt angle of the solar panel will be a lot higher than, for instance, in the summer, when the sun is at the highest point in the sky. Now, as we go on to our testing phase, once we build and assemble our solar panels, as we can see here in this picture, which we have our curved solar panel with a regular rectangular solar panel. So what we did, we put both of them side by side, and for a full solar day, basically from sunup, which right now in the spring is about 7:15 a.m. to about sundown, which is about 7:36 p.m. So we put them both outside from sunup till sundown. And what we did is we connected multimeters to both of the panels to simultaneously measure the voltage and the current. Now, the type of multimeter that we used had a RS-232 capability. What this basically means is that you can connect the multimeter to a computer to monitor real-time measurements. So basically what we go ahead, this is a screenshot of the program itself. So we go ahead and input the time that we want to measure it for, which is basically the 12 hours, and we put an interval to take measurements every 5 minutes. So what the program does is it basically logs the voltage every 5 minutes. So we basically sit there a full 12 hours just to monitor the computer so they don't go to sleep, so that the program does not shut down, so it's a continuous process. And these results are then compared and will be further explained. Now this right here is a chart of average monthly solar radiation data. Now it is important to note that this is not exact. This was compiled from the NEREL website, and it is basically historical data over 10 years that are compiled here in this graph. And this data will be used in our theoretical calculations down the line. And I'll hand it over to Christian, which will further explain some of the results.
Alright, so to confirm our experimental results, we also did theoretical calculations based on this formula here, which is it's based on 4 factors. First is the total surface area of the solar panel, which in our case was 180 inches squared, or 0.116 meters squared. R is the solar panel yield, which is basically the efficiency of each solar cell. And the solar cell used, we got a manufacturer's rating of 14.3% efficiency. H is the annual average solar irradiation, which is usually between 1,000 and 2,000 kilowatt hours per meter squared, depending on the weather conditions, if it's sunny or cloudy time of year. PR is performance ratio, usually between 0.75 and 0.85, also depending on weather conditions, since it's all about the shadings and cloud cover. These are the theoretical results we calculated. For the flat panel, as you can see, for the cloudy and sunny days, it produced significantly less than the curved panel at 0.034 and 0.058 kilowatt hours, respectively. The curve then produced 0.051 and 0.086 for the cloudy and sunny days, respectively. Alright, so this is our voltage graph, which basically the program that we use graphs the data just to show the comparison between the flat and the curve. On the sunny day, obviously both panels are more efficient, and the curved panel produced more voltage both times. Same goes with the current, although on the sunny day the current increase was more significant than the voltage increase. And this is just another comparison graph that shows the current data. This is the power graph. We use voltage and current to find the power, which power is just voltage by current. So we made these plots and integrated under the curve to obtain our energy generation. And as you can see, once again the curved panel produced more power than the flat panel, especially during the early and late periods of the day. This is our experimental results, which once again shows the curved panel producing almost double the amount of energy as the flat panel on both the cloudy and sunny days. The flat panel produced 0.027 and 0.047 kilowatt hours compared to the 0.057 and 0.082 kilowatt hours for the curved panel. This is the percent improvement for the first day of testing for the cloudy day. This shows an improvement of almost 450% at the early time of day when the sun is still relatively low and the flat panel, the surface area does not pick up as much sunlight, and it levels out towards the middle of the day, and then later in the day begins to show a greater improvement once again. For the second day of testing, which was the sunny day, it was also a greater improvement, less scaled down from the first day of testing, but still almost 130% greater during the early hours, and almost 110% for the late hours of the day. This is our error analysis. First, for the cloudy day, the errors are relatively small but greater than for the sunny day. This is because theoretical calculations are based on ideal conditions, and the weather conditions didn't permit for the first day, causing a greater error. Whereas this was easily compared to ideal conditions on the sunny day, which is why the error is less.
To use the energy generated from our solar panel, these are the four components that will be used to use the power. The energy generated from the solar panel will be transferred to the charge controller, which will charge the battery. It will have the power of DC volt. To use the power of DC, you need an inverter to use in a household application, which runs on AC power.
Now, in any design application, there's always room for improvement. In our specific case, we use polycrystalline solar cells. We can easily substitute these solar cells for monocrystalline solar cells that are rated at about 18% efficiency. Now what I've done here is constructed a small table to show you more or less how much of an improvement we can get. So I've taken the results for our results, which are basically for the polycrystalline cells, And note that these are the results taken on the overcast day. So I've taken the data, which Christian explained before, and put them here for both the flat panel and the curved panel. And in the equation that Christian also previously explained, we substituted the solar panel yield instead of the 14% that our polycrystalline cell has with the 18% of a monocrystalline cell. And we can see that for the flat, there's a significant increase as well as for the curve of about, we can say approximately 26% by substituting monocrystalline with the polycrystalline solar cells. Also, a small optimization could also be a better frame. Instead of wood, of course, this is a prototype. It's not the final product. We can use maybe an aluminum frame. And another issue, which is fairly common with solar panels, is temperature. Like the hotter the solar cell gets, the more the efficiency decreases. So keeping solar cells cool would help increase energy generation. Maybe in the near future, we'll see cooling racks mounting on some certain solar panels, maybe even introducing some type of airflow to the solar panels. And this hopefully reducing temperature coefficient can also be done. Observation has shown that, for instance, using monocrystalline solar cells has a temperature coefficient of about negative 0.48%. This basically means that every degree Celsius, for example, over, let's say, 20 degrees Celsius, we would lose about 0.48% efficiency. And for the savings, Mohammed will go over this real quick.
For the economical point of our design, as you can see, the curved panel has more energy generated. And we compared our data with the FPNL per kilowatt hour, which is 10 cents per kilowatt. As you can see, the efficiency of our design is higher, and our rated panel is at 18 watt, and we increased it to 100 watt to compare the savings, which are 80% more than the flat panel. Our cost analysis of overall project is $500, which includes the solar cells, which are a total of 40 cells, cost about $50. And base plywood, another 50, and multimeters. We had 2 of the multimeters, which were computer integrated, which cost about $100. And the other costs, lab costs, wires, came up with a total of $500. And the timeline, you can see, we started in September. We did the research, initial design, planning, and moving on to this January through April, we did the selection of the final design, selecting the material, implementing and constructing of the final prototype. These are our references. We use the questions.
All right, very good. Timing is good. Dr. Bizzle, go ahead, and I have a few.
All right, sure. So I remember you guys, right? I think we had a conversation last time when you presented, and you had a completely different design than you put up now, right? And I made a comment about why you would put solar panels on the reverse side when the sun is in the south of the sky in the northern hemisphere. All three of you guys were very adamant that that was a good design, and the idea was correct, right? Now I see, surprisingly enough, there's no solar panels on the northern side of your design, right? That's fine. Make design changes, right? My main concern with your design or your specific project at the moment is I don't really see any beef or any analysis to it. Maybe Risha, you should stop the camera or something.